So let's get into some of the techniques of solving equations. When we have an equation like this, a lot of people have the habit of subtracting 3 from both sides by writing it underneath, as if we were doing 3 minus 3 and 10 minus 3 on our scratch work. And really that's okay. X plus 3 minus 3, these add up to 0. We could think of 3 minus 3 as 0. So x plus 0, that's just x. 10 minus 3, 7. We're done. I'm not a huge fan of this every time, because if we get something like this, and then I put in a minus 13 here, 13, negative 13, okay, that gives me an x. 10 minus 13, I'm not really lining it up this way. Now I've got to borrow, well, no, 13's bigger than 10, right? I really have to line it up this way. 3 minus 0 is 3, 1 minus 1 is 0. I've got a negative 3. A lot of people run into trouble when their subtraction is written in the vertical way, but their second number is the bigger one. Or, let's say we start with a negative number. And then I put in my minus 13. 13 minus 13, great. Negative 10 minus 13, I have to recognize these are both going in the same direction to get negative 23, right? Negative 23 plus 13, moving me closer to 0, but not as far as 0. Where do I end up? I end up at negative 10, right? Negative 23 is the solution to this equation. But when I have a minus 13 here, I can tend to think in terms of subtraction. I think it's going to be better in the long run if we get in the habit of adding the opposite and being comfortable with simplifying algebraic expressions, not just in doing vertical second grade arithmetic. That can also get us into trouble if we have something like 13 minus x. I see this minus here, and I want to do the opposite, which is add. But I have to see, if I'm going to add, what I have to add is x, right? If I add 13 here, 13 plus 13 is 26. The x is what's moving backwards, so instead of adding 13, I can add x. Well, I don't want to line it up with the 13, so I've got to move that over so it's lined up with the x, and then I go over here, plus x, this cancels, 10 plus x, I haven't improved anything. I've made the x positive, that's good. But I still have two unlike terms here. 10 plus x is not 10x. 10 plus x is not 11x, right? This isn't 10x's plus one more x. These are unlike terms. Recognizing those unlike terms is, for many people, easier when it's written horizontally here, and it looks like an expression with multiple terms. If you are going to line it up underneath, make sure you're lining up the like terms with the like terms. You're not putting this 13 under the x or anything like that, right? Our goal is to get all the x's together. We only had a single x here. There's no reason to move it. And all the constant terms on the other side, so I can get something like x equals a number. Now that I've moved the x over, I'm not going to subtract 13. If I do that, I'm going to line it up with the 10, not with the x, right? 13 minus 13 doesn't disappear. 13 minus 13 is 0. 10 minus 13 is negative 3. and then the plus x is still plus x. Right? My answer is not negative 3. My expression is x plus negative 3 equals 0. So now I've got to come back, add 3 to both sides. 0 plus 3 is 3. Negative 3 plus 3 is 0. 0 plus x is x. If I want to show all my work here. I think it would have been a lot faster and we need to be able to see both versions of it here. To isolate the x by first getting rid of this other term here, so minus the 13. And I get negative in front of the x. Negative x equals 10 minus 13, negative 3. And then I cancel this negative. Well, negative x is negative 1 times x. So if I multiply this by negative 1, the opposite of negative x is positive x. The opposite of negative 3 is positive 3. X equals 3. Right? I have the same answer. A little too far here. There we go. I have the same answer either way. This just went through more work. 1, 2, 3 operations instead of just 2. Takes up more space on my page. Right? You want to just be paying attention to how can I get identities, either additive or multiplicative depending on what's going on. Get identities that cancel out in order to get my variable by itself and the number by itself. Now, another situation where this can be challenging is when we have fractional coefficients. Just like I don't like writing the minus underneath, when we have whole numbers here, dividing as an inverse operation to multiplying, that works fine. We get x equals 12 divided by 2 is 6. All right. But what am I going to do over here? Complex fractions, that is, a fraction that includes a fraction as part of the numerator or denominator, are kind of ugly. It's not clear what's going on here. It's much easier to always use the reciprocal. Right? 2 times x, how do I cancel that? I multiply by its reciprocal. 2 halves is 1. If I'm multiplying this by half, I'm multiplying this by half. What's half of 12? It's 6. The same thing is going on here. X times 2 divided by 2, the 2's cancel. Same exact situation as this problem. But x is also being divided by 3. How do I undo division? I multiply, right? The 3's cancel. 3 halves of 2/3, that's the same as 2 halves of 3/3, which is 1 times 1. It's just plain x. If I multiply this by 3 halves, I need to multiply this not by 1 half, but by 3 halves. Right? I need the 2 to cancel and the 3 to cancel. I can do that in one big step instead of 2 small steps. Now, when I have 12 times 3 halves, I have a choice. I can associate the 12 with the 3, get 36, but now I have to take 36 divided by 2. That can be a little challenging depending on how big those numbers get. Right? 36 divided by 2 is 18. That works. It's often going to be easier if this does cancel to do the division first. Half of 12 is 6, or 12 divided by 2 is 6. 6 times 3 is 18. If you can cancel, do so, and then multiply. Whether we're in the context of solving equations or whether we're just doing the fraction arithmetic. If you can't cancel, if this was 3/5, then we have no choice but to do 12 times 3, 36 divided by 5, and that would be our answer, 36 fifths. So multiplying by the reciprocal when we start with a fraction, or when we start with a whole number, or for that matter, if I started with a fraction, what's the reciprocal of 1/3? 3 over 1 times 3. 3/3 is 1, so that's 1x, which is x. There's my 36, and I'm done, right? Multiply by its reciprocal. You don't need to put anything over 1. 3/3 is 1, and there we go. 12 times 3 over 1, that's silly. 12 times 3, 36. Here we need the 1 over 2 to show the 2 is in the denominator, so that it's canceling with the numerator. 2 halves makes 1, right? We can just always use the reciprocal to cancel that original multiplication. Now, what if we have fractions on both sides? It's not really so different. Here we definitely don't want to just divide by 2/3 on both sides. Multiplying by the reciprocal. 2 cancels, 3 cancels, 1 times 1 times x is just x. I could do 13 times 3, but wait, 3 cancels with 6, right? 6 is 2 times 3, so the 3 cancels. I just have 2 times 2, which is 4, and 13 doesn't cancel with anything. 13 is just left there. Instead of doing 13 times 3 is 39, 6 times 2 is 12, then I have to reduce, that's 3 times 13, that's 3 times 4. Right? That works, but this step tends to get challenging, right? Cancel first. If you want to write out the factored form, right, write 6 is 2 times 3 to make that obvious. That's not a bad idea. We're still getting 2 times 2 in the denominator. Okay. Now what do we do when we have fractions and other operations all in the same problem? Let's say, let's use black. Let's say 2/3 x plus 13/6. We'll put one whole number in there. Right? Now, we have one term with x in it, and a constant term equals a constant term. If I want to get x by itself, whether this is a fraction or a whole number, I want to get rid of this other term. I want it to be x plus 0. So how do I get plus 0 here? I use the additive inverse. (13/6) plus the opposite of 13/6, that's 0/6. 0/6 is 0. 0 plus this thing is that thing. So I'm back to 2/3 x by itself. Now over here, this is a bit annoying. 5 is counting wholes. That's a different unit than sixths. So I need to multiply by 1 so I can get 36 plus negative 13/6. Now I have the same unit, so I can do 30 minus 13. 30 minus 10 is 20. 20 minus 3 is 17. Right? If I want to do that arithmetic off to the side, 10 minus 3 is 7. 2 minus 1 is 1. There's my 17/6. The forward number was the bigger one. 30 is bigger than the negative 13, so I have the positive. Now I just have an x term on the left and a constant term on the right. I'm going to multiply both sides. Not by 6/17, right? I don't care if the 17 cancels. I'm not trying to get 1 over here. I'm trying to get 1 times x over here, right? My goal is to get x by itself. So I want this to become times 1, this to become times 1, and then that 1 times x is just plain x. Again, just like on the last problem, instead of doing 17 times 3, I recognize 3 cancels with the 6. That's 3 times 1, that's 3 times 2. So I have 17 over 2 times 2, 17 over 4. Now, this is correct, this works, this is fine, but it's kind of annoying to have to get a common denominator in the middle of my problem. As we get to more complicated versions of this with a bunch of fractions, all of that fraction arithmetic is kind of distracting, right? This process of getting 17/6 took a little bit of concentration, took a little bit of our attention away from the general problem. So there's another way to deal with these kinds of equations. Two-thirds x plus 13/6 equals 5. And the way to deal with this is by introducing the same new operation to both sides, but not starting with addition or subtraction. I'm going to introduce the operation of multiplying this expression by 6 and multiplying this expression by 6. Now, why did I put these parentheses in here, right? 5 times 6 doesn't need parentheses. When we did multiplication before, no parentheses for any of these examples, right? The difference is, for all of these, the only operation here was multiplication. And multiplication is associative. So a half times 2x is the same as a half times 2 times x. But in this example, I have 2 separate terms. I'm not just multiplying this term by 6. If I'm multiplying this expression by 6, I have to multiply this entire expression by 6, right? We're introducing the same new operation to both expressions. Now, once I have all of this times 6, I can go ahead and distribute. 6 times 2/3 x and 6 times this other thing equals 5 times 6. And now I can do all that multiplication. 6 divided by 3 is 2. 2 times 2 is 4. 6's cancel outright. Fantastic. 5 times 6 is 30. I still have a number times x plus another number equals some third number. Right? It doesn't really look simplified, but I don't have denominators anymore. I'm no longer trying to deal with common denominators and adding and multiplying fractions. Everything is whole numbers, and so it looks easier. Right? So now I can go ahead. Come on. I can go ahead, add the opposite of 13. 4x plus 13 minus 13, that's just plain 4x. 30 minus 13, that sounds familiar. And then at the end, instead of multiplying by 3 halves, I've already multiplied by that 3. I'm just dividing by 4. And since it's a whole number, I can get away with writing the just division version of it, 17/4. Right? I might still get a fraction as my final answer, but by multiplying both sides by an appropriate number, I can get to a version of the equation where the rest of the introducing the same new operation and simplifying is a little bit faster. Right? So that begs the question, where did this 6 come from? Well, hopefully you noticed it's what's going to cancel the 3 and the 6. If I have a similar looking equation, like 2/3 x plus 13/7, I'm not going to multiply by 6. I'm not going to multiply by 7. What do I have to multiply by? That's right. I want this denominator to cancel and this denominator to cancel. So once I get my 21 times 2/3 x, 21 times 13/7, 21 divided by 3 is 7, 7 times 2 is 14. 21 divided by 7 is 3, 3 times 13 is 39. 5 times 21, well 5 times 20 is 100, plus 5 times 1 is 5, 105. I don't have to do 5 minus 13/7, deal with common denominator, and then multiply by a reciprocal. I have all whole numbers here, so I can more quickly than usual. Let's see, 100 minus 30 is 70. 75 minus 9 is 65, 66. Now since it's a whole number, I can just do over 14 instead of having to do times 1/14. Or if you like being consistent, which I should encourage you to do, times 1/14. Now you notice 66 and 14 are both even, right? So I am still going to have to reduce. 66 is 2 times 33. 14 is 2 times 7. So I get x equals 33 over 7. Or the solution is 33/7. I still end up with the fraction. I still have to reduce, but it's maybe a little easier than getting that common denominator. One other quick note here. When we have an equal sign and another equal sign, we're saying that all of these are all equal to each other. Whenever we have an equal sign, we're saying the entire expression is equal to what comes after it. So we have to be very careful. I never start going sideways until I'm just simplifying a single arithmetic expression here. Right? I'm not saying this whole expression is equal to 39. This term equals 39. But it's also being added to this term over here. Right? So you're never going to write 21 times 2/3 equals 14 equals plus 21. Right? Your equal sign stays lined up here, mostly, right? Kind of lined up here. You want to try to keep it as lined up as you can. And you're simplifying this expression. Has nothing to do with what's going on over here. We're simplifying. Now we're introducing a new operation to both sides. Then we simplify this one, right? It's staying as two separate pieces there.